Okay, so let's get started. So we were looking into large Eddy simulations. So we saw the difference between filtering and resolving, and we understood what is, the conceptually we understood what is subgrid scale when we talk about it, and what we mean by residues. So we look at the governing equations today. So essentially, the governing equations are, we have to start from first principles, Navier-Stokes equations, and filter it. So what we have is filtered Navier-Stokes equations. Filtering is nothing but your volume averaging or low pass filtering. Okay, so we start with Navier-Stokes incompressible form. So that's the Navier-Stokes equations. We now perform the filtering operation on that. Okay, so the over bar represents filtering. So now, unlike Reynolds averaged equations, Reynolds averaged Navier-Stokes, where the ensemble averaging and differentiation they commute. Whether you take the derivative of a mean quantity, ensemble mean quantity, or you take mean of the derivative of that quantity, both are same. So we could move the overbar operation in RANS inside the differentiation operator. It was dou by dou t of ui bar. Okay, but that is not the case here. Here overbar, as I said, overbar represents filtering, volume averaging. Okay, so that means we have two types of derivative here, a spatial derivative and a temporal derivative. So what about the first one, temporal derivative and spatial filtering? So volume averaging is nothing but spatial filtering here, right? So the dou by dou t term and the filtering, they actually commute. That's because the filter volume or your control volume is not a function of time, right? So note that filtering and derivative with respect to time it is the dou by dou t term commute. So we can move this filtering operation inside the operator here. That we can see the illustration is straightforward. So if I have dou ui by dou t term filtering, I can write this as the actual filtering operation, which is volume averaging 1 by v is the volume, integral v dou ui by dou t dv. Okay, the volume averaging part here. So this is nothing but, now I can take out the time derivative outside, dou by dou t of 1 by v integral v ui dv. That's because volume is not a function of time. since volume is not a function of time. So this is nothing but dou by dou t of ui bar, filtered velocity. Okay, so this is good so far. The temporal derivative part was fine, but the spatial derivative will create a problem. So the question is, what about spatial derivatives? The answer is not straightforward because there is an exception for it. So in general, they don't commute. The filtering operation over this dou by dou xi, dou by dou xj terms, they don't commute, so I cannot move the filtering operation over the primitive variables. So in general, filtering and the dou by dou xi, the spatial derivative, do not commute. So in general, so there is an exception which is a rare. So the exception is only when you say I am using a homogeneous filter. Homogeneous filter implies constant grid size. You have made a mesh which is equidistant everywhere. Only in that case, you can move this filtering operation inside. Okay, so exception is homogeneous filters. Where the control volume size is constant. You are essentially performing a filtering operation over the mesh. Okay, sometimes the filter size can be same as mesh size, sometimes it may not be, that's your choice, but the filter size cannot be smaller than the mesh size, right? You are volume averaging the data, so it can be same as the mesh size or larger than that, right? 2 times, 4 times, like that. So if CV size, your control mesh size is constant, then this can be an exception, right? That is a bit rare. In engineering problems, we cannot afford to have equidistant mesh or having a control volume size constant everywhere, right? That is uniform grid spacing. That is an exception. In all the engineering problems, it is common to have a stretched mesh. Okay, so in general we cannot do this. So what is the way out? We don't even have a governing equation ready for us without even solving it, right? Let's take any spatial derivative term. Phi can be pressure or velocity or anything. So dou phi by dou xi filtering, this is nothing but 1 by v integral v dou phi by dou xi dv. Okay, so now as I already said, this volume however, this volume in general is a function of your spatial coordinate, except that CV constant, right? Exception in that case. So what do we do? There is actually a numerical way out. It's like a stalemate here. We cannot even have a governing equation ready. One way of achieving the governing equation here is that have a numerical solution, and this particular solution is actually provided by Gosel and Moin 1995. Okay, they showed that the dou by dou xi, the spatial derivative term, can be moved out of the integral with a numerical error, which is equal to order of magnitude delta square. Delta is your mesh. Okay, so if you are afford to live with that, you can actually move the dou by dou xi outside the interval. So with that, what we achieve is, if I follow this, I get essentially this dou phi by dou xi average, sorry, dou phi by dou xi filtering is equal to, now I am now moving the spatial derivative outside. So I get 1 by v integral v phi dv plus the error. Okay, so that is equal to dou phi bar, the filtered variable phi bar, by dou xi plus the error that is being introduced. This error is omitted out in LES. Okay, this error is or this numerical error, neglected in LES, because we essentially want dou phi by dou xi filtering should be equal to dou phi bar filtering by dou xi. We want to substitute this left hand side with this particular term dou phi bar by dou xi. This is omitted, but this delta is now a function of your mesh. Okay, in a DNS, the mesh size will be as tiny as, let's say, the Kolmogorov microscale, so the error is tiny, but not in LES. The whole idea of LES is actually to model those small scales, considering they are statistically isotropic, so that we can have a larger mesh and it will be economical. Okay, so it's somewhere in between, a technique in between RANS and DNS. RANS and DNS are two extremes. DNS where everything is captured, RANS where DNS is where everything is captured, and RANS is where every turbulent scale is modeled, and LES is somewhere in between. Partially you are capturing some of the turbulent scales, the large scales, and the tiny scales are modeled, right? So in this approach then, the mesh size is not very tiny. So this error, which is a function of delta square, is not that small. Okay, so we can say that this error is not very small. Since delta or the mesh size is coarser in LES when compared to the DNS mesh. So for the error is not that small here, but anyway, that is the path we have to follow ahead. So now I can, with this numerical error being omitted, I can have the governing equations ready. Okay, so I can use both these two. Let's call this equation 2 here. So using this 1 and 2, equation 1 comma 2, we get the full filtered governing equation. Okay, so I get dou ui bar by dou t ui bar is a filter velocity plus dou by dou xj ui uj over bar. So it's a filtered product of velocities equal to minus 1 by rho dou p bar by dou xi, that is the filtered pressure, gradient of filtered pressure or result you can say, plus nu dou square ui bar by dou xj square. So you have got your filtered Navier-Stokes equation. Is there a problem you see with this equation? Something that you have to, if you want to calculate using CFD, is there something missing in this equation? So what does a general transportation looks like? And do you have all these terms inside this equation? Let's call this equation 3. Sorry? And this is a Navier-Stokes. I'm not talking about general transport equation. Do you remember general transport equation? What does it constitute? How many terms are there in it? 4. What are they? Unsteady term, that's there. Convection term, is it there here? Yes or no? Where is it? Is that a convection term? There is a filtering, it's a single term. There is a filtering of the velocity products. There is no convective term here in this. It is not ui bar, uj bar, right? I cannot use product rule here to bring the convective. What is being convected? To actually prove that, you have to go to a non-conservative form and to tell that what is being convected, right? So an advection velocity or convection velocity comes out of the derivative. I cannot use product rule here to do that, right? So there is a problem here in this equation, right? So this equation does not have a convective term or advective, if you want to call that. So we want to write it in a general transport equation where convective fluxes are there, diffusive fluxes are also there, okay, unsteady term is there, and then source terms, but it doesn't have. So what do I do is I add the convective term here, okay, add the convective term. So add dou by dou xj ui bar uj bar on both sides. This I am adding the convective term. If I do this, I get dou ui bar by dou t plus I have dou ui uj over bar by dou xj plus this particular term equal to minus 1 by rho dou p bar by dou xi plus nu dou square ui bar by dou xj square plus I am adding the convective term. So rewriting this in the standard form of a general transport equation, I get dou ui bar uj bar by dou xj. I am moving this particular term here, the second term, onto the right hand side. So I get minus 1 by rho dou p bar by dou xi plus nu dou square ui bar by dou xj square. Now I have this particular term minus of this, the two red terms here, right? So the convective term on the right hand side minus this, not the two red terms, sorry. So this particular term minus ui uj over bar is being moved to the other side. So that means I can write this as plus dou ui bar uj bar by dou xj minus dou ui uj over bar by dou xj, or I can write this as, these terms remain the same, I can write this as minus dou by dou xj of ui uj over bar minus ui bar uj bar. Now this particular term inside the bracket is called tau tau ij sgs. This is an unknown here. In LES you are computing for filtered velocity and filtered pressure, not for the filtered products of the velocities. Okay, so this is an unknown term, and therefore this unknown term minus ui bar uj bar, this entire part is an unknown. Okay, so note that in LES you compute ui bar and not ui uj over bar. Okay, so therefore ui uj over bar is an unknown. So I have 6 unknowns here. So this is an unknown. Again, turbulent closure problem. The tau ij sgs, right? So this tau ij sgs is popularly called subgrid scale stresses. Subgrid scale stresses, sometimes also called residual stresses, but subgrid scale is better because we know that it's the residue is not exact in LES. Okay, or residual stresses. So this is an unknown that requires modeling. This demands modeling and popularly called SGS modeling or subgrid scale modeling. So you are going to model only those quantities. So again, this is not a stress, even though we are calling it as stress, just like Reynolds stresses. This has unit, this particular term, as you see, we are writing dou by dou xj of nu dou ui bar by dou xj, the viscous stress. So it is written in that fashion. So the units comes out to be stress. So it's not really a stress. Okay. So not really a stress term. You can call this as subgrid scale motion. This particular term is accounting for all the when you filter it out, you get that residual fluid motion or subgrid scale motion. So accounts for subgrid turbulence. Subgrid turbulence, that is the turbulent eddies that are smaller than your mesh size. That has to be going into tau ij SGS. Okay.